Hi, welcome to Quantum Academy for Physics. I'm Swapna and I'm teaching you mathematical physics. In differential equations, in last class we have learned about linear differential equations, how to solve a solution for linear differential equations. And Bernoulli's equation. Bernoulli's differential equations and how to solve a solution for first order and first degree differential equations using variable separable method. And exact differential equations, how to solve a solution for exact differential equations and homogeneous equations. Homogeneous differential equations. Using these methods we have find the solutions for first order and first degree differential equations. Now in this class, today's class, we will learn to find the solution for higher order differential equations. What is higher order differential equations? The standard for solution higher order differential equations. We will find a solution for higher order differential equations. Higher order, that means the order of a differential equation is n. I'm taking n and a degree will be 1. The standard form of the higher order differential equations, and this higher order differential equation is a linear differential equation. The standard form is d power n y by dx power n plus p1 into d power n minus 1 into y by dx power n minus 1 plus p2 into d power n minus 2y by dx power n minus 2 plus and so on plus pn into y equals to x. This is the standard form of a higher order linear differential equation. Here p1, p2, so on pn are the functions of x, and the standard form of a linear differential equation with constant coefficients are d power ny by dx power n plus k1 into d power n minus y by dx power n minus 1 plus k2 into d power n minus 2 by dx power n minus 2 into y plus and so on plus kny equals to x. Here k1, k2, so on kn are constants. Remember these two differential equations. Here p1, p2, p3, so on pn are variables, and here in this equation k1, k2, kn are constants. This is a linear differential equation of higher order, and the order will be n and the degree is 1. Here in these equations we have the coefficients of the derivative are constant. The coefficients of derivatives are constants and the degree will be 1 and the order will be n. These two are linear differential equations. For simplicity, I will replace these derivatives with the d, operator d. every time writing d power n by dx power n, d power n minus 1 by dx power n minus 1 is little bit difficult. For simplicity, I will replace this d power n by dx power n with d power n, and d power n minus 1 by dx power n minus 1 with d power n minus 1, and so on. I am taking dy by dx as d into y. We have derivated y with respect to x for once, so I have taken d power 1 into y, and d square y by dx square is d square y, dq y by dx cube as dq y, and so on. And now replace these terms in a linear differential equation by these terms. The equation will be f of d into y equals to x. This is capital X, this is right hand side, and this is left hand side. Now f of d will be d power n plus d1 power n minus 1 into constant k plus and so on plus kn. For understanding, I am giving one example: d square y by dx square plus 2 into dy by dx minus 3y equals to 0. This can be written as d square y by dx square is d square y. D square y, I am taking y as common. 2 into dy by dx is d into y minus 3, y is common, which is equal to 0. Now we can easily find the solution for a linear differential equation of this type. And if in equation of a linear differential equation with constant coefficients, take this as equation 1 and this as equation 2. Now here x is nothing but x is function of x. I am rewriting this equation: f of d into y equals to f of x. Remember this equation, this is left hand side, this is right hand side. If f of x equals to 0, that is right hand side is equals to 0, then f of d into y is equals to 0. Then the solution of these equations will be y equals to complementary function. Solution will be in terms of complementary functions. This type of equation, if right hand side of a linear differential equation is equals to 0, then that equation will be said to be homogeneous equations, homogeneous differential equations. And if the right hand side is not equal to 0, that is f of x is not equal to 0, and the differential equation is f of d into y equals to some pi of x, then the solution for this type of differential equations will be y equals to complementary function plus particular integral. CF is complementary function. Complementary function pi is particular integral. These type of equations, that is when right hand side is not equal to 0, then these type of equations, differential equations, is said to be non-homogeneous differential equations. Now we will find solution for a homogeneous and non-homogeneous differential equations. I will explain by giving examples. So these are the say higher order differential equations. Now we will solve problems for second order and first degree differential equations. First degree differential equations. If the right hand side of a differential equations of second order and first degree is equal to 0, then that differential equation is said to be homogeneous differential equation. And second order and first degree differential equation can be written as d square y by dx square plus dy by dx into p plus q into y equals to x. If this x is equals to 0, then this equation can be written as d square y by dx square plus dy by dx into p, where this p is a function of x, plus q into y, q is a function of x equals to 0. This is a homogeneous differential equation. Homogeneous differential equations. And we will find the solution for homogeneous differential equations of second order and first degree differential equation. For homogeneous differential equation, the solution will be a particular integral. Y is a complementary function. The solution will be a complementary function. Now, how to find this complementary function for a homogeneous differential equations? We have few methods to solve a solution, to find a solution for homogeneous differential equation. We will learn one by one. I am writing the homogeneous differential equation using an operator method, that is d power n plus k1 d power n minus 1 plus k2 d power n minus 2 plus and so on plus kn, which is equal to 0 into y. Now the coefficient of y is equal to 0, right? Take coefficient of y is equal to 0. The coefficient of y is d power n plus k1 d power n minus 1 plus k2 d power n minus 2 plus and so on kn equals to 0. Now this equation is said to be auxiliary equation. First of all, to solve a homogeneous differential equation, you have to take the auxiliary equation from a given differential equation. Now then solve this auxiliary equation for roots. The roots of this auxiliary equation will be m1, m2, m3, so on mn. These are the roots for a given differential equations. First of all, we have to take the auxiliary equation and then find the roots. Now first method, if the roots are real and distinct, if all the roots are real and distinct, then the complementary function will be written as c1 e power m1x plus c2 e power m2x. If the roots are real and distinct, then the solution for the given differential equation is c1 e power m1x plus c2 e power m2x. Second rule, if the roots are complex. If the roots are complex, that is exists in pairs, and in the pair, and in that pair one root will be real and the other root is imaginary, then the complementary function will be written as e power ax into c1 cos bx plus c2 sin bx. Remember, I am giving the rules for second order first degree homogeneous differential equations. Third rule, if the roots are real and distinct in opposite sign, that is, if the roots are same but with opposite sign, then the complementary function will be written as m2 equals to, if the roots are m2 equals to minus m1, then the complementary function will be written as c1 cos hyperbolic m1x plus c2 sin hyperbolic m1x. Now fourth rule is, if the roots are real and same, if the roots are real and same, that is, if m1 equals to m2 equals to m, then the complementary function can be written as c1 plus c2x into e power mx. These are the methods to find a general solution, this complementary function for a second order first degree homogeneous differential equations. Now we will solve few problems for easy understanding. First problem, solve d square x by dt square plus 5 dx by dt plus 6x equals to 0, given the boundary conditions as x of 0 equals to 0 and dx of 0 by dt equals to 15. Now rewrite this differential equation as d square plus 5d plus 6 into x is equals to 0. Now find roots for this equation. The formula to find root is minus b plus or minus under root of b square minus 4ac by 2a. Here in this equation, a, the coefficient of d square is a, which is equal to 1, and coefficient of d is 5, which is equal to b, and the constant term will be equal to c, that is 6. Now substitute in this formula. We have minus 5 plus or minus under root of b square is 25 minus 4ac, 4 into a is 1 into 6, 6 4 is 24 by 2a is 2, which is equal to minus 5 plus or minus under root of 1 by 2. This can be taken as minus 5 plus 1 by 2 and minus 5 minus 1 by 2. Minus 5 plus 1 is minus 4 by 2 minus 6 by 2. This is, the roots are minus 2 and minus 3. So m1 is minus 2, m2 is minus 3. Now the complementary function can be written as the roots are real and distinct, we have c1 e power minus 2x plus c2 e power minus 3x. Now taking the boundary conditions, x of 0 equals to 0. Sorry, here we have derivated x with respect to t, so take t power m1x and e power m2x. E power m1t into e power m2t here. Now x of 0 is 0. This 0, x of t is 0. Here t is equal to 0. X of t is x of 0. Here t is 0. Now from this equation number 2, here this is x, actually x into CF. Now x of t is equal to 0, which is equal to c1 e power minus 2 into 0 plus c2 into e power minus 3 into 0, which is equal to c1 into e power 0 is 1 plus c2 into e power 0 is 1. From here c1 equals to minus c2. And from second boundary condition, d into x of 0 by dt is equals to 15. For this to apply this boundary condition, we have to derive equation number 2 with respect to t. So dx by dt equals to c1 into differentiation of e power minus 2t with respect to t is minus 2 into e power minus 2t plus c2 into minus 3 into e power minus 3t. Now dx by dt will be equal to minus 2c1 e power minus 2t minus 3c2 e power minus 3t. Now from boundary condition, we have this will be from here t is equals to 0, which is equals to 15. Dx by dt equals to 15 equals minus 2 c1 e power 0 is 1 minus 3 c2 e power minus 3 minus e power minus 0 will be 1. Now substitute c1 is equal to minus c2 in this equation. 15 equals to minus into minus plus 2c2 minus 3c2. Now solve this. We have minus c2, 2c2 minus 3c2 will be minus c2. So we have c2 equals to minus 15. Now substitute c2 in this equation. We have c1 equals to 15. c1 equals to 15 and c2 equals to minus 15. Now substitute c1 and c2 values in a complementary function equation. Now complementary function will be equal to c1 e power minus 2 t plus c2 e power minus 3t. Actually this is a complementary function. Now substitute c1. We have c1 as 15 and c2 as minus 15. Now substitute in this equation. Complementary function is 15 e power minus 2t minus 15 e power minus 3t. This is the general solution for the given homogeneous differential equation. Now take one more example. Now write this equation into auxiliary form, that is d square plus omega square into y equals to 0. The auxiliary form is of this equation is d square plus omega square equals to 0. Now the roots from this equation will be I plus or minus I omega, that is this is in the form of a plus or minus ib. Here a equals to 0 and b is omega. The complementary function for the root containing imaginary and one real value will be written as e power ax into c1 cos bx plus c2 sin bx. Now complementary function will be, here a is 0, so e power 0 will be equal to 1, c1 cos b is omega x plus c2 sin omega x. This is a complementary function. After completing the differential equations, I will solve previous question papers for differential equations, and in the next class we will learn to solve particular integral and complementary function of a non-homogeneous differential equations. Please don't forget to subscribe to my channel Quantum Academy for Physics, and if you have any doubts please comment in the comment box, so that it will be easy for me to clear your doubts. And don't forget to click on the bell icon for daily notifications regarding my videos. Thank you.